some stuff to tell you. Got one mathy thing to tell you today, and then I thought we would take the rest of the time to work on the number of things that are floating about to be done in this class that still probably haven't been done. We'll find out. It's all good. We'll figure it out. Let's do the most important thing we can possibly do, and just be here. Good way to start the day. Yeah, it is time. Still going. It's okay. Need to get some WD-40 for that door. All right. Let's see, who was that?
That was me.
It was you. It was you.
I opened it. I was like, oh, it's really quiet. And then I was like, closing it.
I'll try to remember to bring some in. All right, friends. So we've got a web work that I extended through tomorrow. Web work, planar systems 2. It's got generalized eigenvalues. I looked at that. I actually got a question about it. And then, thanks to that question, realized, okay, well, I would love it if everyone did this assignment as opposed to not. So I extended it. I think through tomorrow should be good. There's only 4, I think there's only 4 problems. Yeah, 4 problems. Happy to consult on that today. We'll do a little consultation. There is also an assignment due next Monday, which is 3 planar systems to sketch out. So let's talk about that really. Has anybody done that? Is anybody done with that homework? Good. That's good. That makes me happy. Because I'm gonna give you some time today to work with consultation. Here, haircut. You get a haircut? Your hair looks good. So those 3 problems are in the calendar. If you're not sure where they're at, someone earlier was not sure how to find those, look at the calendar and it'll say homework, whatever, due next Monday. There's 2 of those that are just general planar systems. The only way I want you to do those is with the tau delta plane classification system, as we talked about. So if you have not watched last Wednesday's lecture, you need to, because there was a lot of shit that went down and it's all about this. And if you haven't computed this quantity for those things, then you have not done them the way I would like you to do them. So there's a 1 and a 2, and these are just general systems. I won't take away the fun. And then number 3 is a relationship problem. Part of the grade for this is you write me a story. Okay, just a short story. I want to hear, what are these people like? So what are the personality types? It doesn't have to be an opus, but it has to exist in some form. And then relationship predictions, possible relationship outcomes. The more you do here, the better it'll be, but don't get crazy. So there's an R and a J in that. Make them whatever names you want. Have fun. I hope you have fun. You guys look like you're having a great time right now. So keep that up. Keep up that high energy spirit. But that's due next Monday currently. Does this all sound good? Cool. Wednesday of this week, we are starting nonlinear systems. So everything we have done are linear planar systems. On Wednesday, super important day, very pivotal day, we're going to do nonlinear systems. This is where things get interesting. This is where not everything is happening at the origin. We're going to have face portraits that maybe have something at the origin, but then maybe there's a spiral out here. So we'll have some things that the behavior can be much more complicated in stages in these kind of systems, and they're more realistic. But we use this as a microscope. This is linearization. Derivatives are mathematical microscopes. And you're going to see that in full glory as we do this. So it definitely would help to get started on these before Wednesday, if you can. I want to do one thing, and then I'm going to give you time to work. But I want to set up for Wednesday. So I want to talk about a biological model of competition. So biological model competition. This is often called, well, it's probably more often called, a Lotka-Volterra model of competition. There's no weird, that's just an O. So I'm going to tell the story today so that when we come in on Wednesday, I can just get rolling on it and I don't have to do the story. But I want to set the model up, and then we'll come in and talk about how to analyze the full system. So for this, we're going to have rabbits. I'm not going to use R's and S's. I'm just going to use X's and Y's here. But X at T equals the population of rabbits in some limited space. So, and then let me draw the picture in a minute. Y of T is the population of sheep. So there's actually no predatory interaction here. The sheep aren't eating the rabbits. They haven't become carnivorous zombie sheep that are just, gobbling up every bit of flesh they can find. They're just competing for a limited resources. So we have limited grass supply. They live in a little fenced in area, big fenced in area, whatever. There's a finite amount of food for them to get. So one of the things that's going to happen here is, first off, rabbits multiply faster than sheep. We're going to take that into account. So the growth rate of rabbits is in general higher. Sheep probably win out on any interactions between, so like a sheep and a rabbit are trying to eat the same piece of grass. Sheep wins. Sheep just pushes the rabbit out of the way. So the sheep will beat out the rabbits. The sheep will beat out the rabbits when they're competing. They have an edge on getting the resources. So the model's going to look like this. So I'm going to start off with an x dot. So this is the velocity of population. This is the rate of population change, rate of rabbit growth. We're probably going to want to think of these as in the hundreds or thousands. Let's just say that. Both these units are in the hundreds. It's going to look like otherwise it'll look like there's 3 sheep, 3 rabbits, and 2 sheep. We're talking lots and lots. So x dot, this is the rate of rabbit growth. And it is going to be proportional to, and I'm going to put these up and then explain them. And then this is going to be 1 minus x minus, I got to double check on it. 3 minus x minus 2y. I'll tell you why. I'm going to explain it. That's what I want to do today. I'm not going to do anything other than explain why these equations look like they do. There we go. Cool. Okay. So in the absence of the other population, let's just think about how these things grow. They grow according to what's called a logistic model. So in the absence of the other species, each species grows according to a logistic model. Logistic models show up everywhere. In chaos theory, if we're going to talk about that, I feel like at some point I have to talk about chaos this semester. I don't know how. I can't talk about it because this might be your last chance to ever hear about it. But yes, Lou.
Since we're talking about populations, you could do the model where it's like annual population of like the deer, and then it like fluctuates in between.
That's exactly this model. Yeah, with a growth parameter on it. So that's exactly what I was thinking about. So yeah, great minds. You have one. I'm not going to claim I have one. I've just been doing this shit for a long time, exclusively. So in the absence of the other species, each species grows according to a logistic model. So let's just say, there's no sheep. Then the growth rate of the rabbits, or the growth of the rabbits, is modeled by this system. And we did this kind of stuff before. Right now, I'm just assuming y is equal to 0 here. So y equals 0. And so that's the model for the rabbit growth. I got to make sure I'm calling the right things. Remember how we did that? Well, we did this little phase line. So that's a one-dimensional system. And we've done this stuff. We did a lot of this stuff. If I plot this out, it's a parabola that looks like this. This is 3. And as I said before, it's not 3 rabbits. It's like maybe 300 or 3,000 rabbits. So think of this as in large units here. But the growth model looks like this. This is a logistic model. Notice that if y equals 0, change these two around. Sorry, this won't change the equation, but I want the order to be the same so that they make sense visually. So if x is equal to 0, this y dot is equal to y times 2 minus y. Very similar. It's just a parabola that intersects at 2 as opposed to 3, but kind of the same rhythm. So this max number here, remember x is the population. This is the max population possible. Because we're not going to think about negative populations. This is called the carrying capacity of the population. So the carrying capacity is something that's dependent upon the resources and the consumption of the critters consuming those things. It's just the most the environment can sustain. Here, the carrying capacity we could say is 3. Here the carrying capacity would be 2 there. So in other words, and that makes sense, let's just put it up here. If I just did y dot, if I assumed x equals 0, then y dot equals this. And its 1D model, y dot versus y, looks like this. It's 2. Rabbits are smaller. There's about 50%, we'll just say 50% more rabbits can be held in that environment. So here the sheep have a smaller carrying capacity, 2,000 versus 3,000. Does that make sense? Got a fixed field, can't have as many sheep as I have rabbits living there. When you reach carrying capacity, population growth stops. Remember this is the rate of growth. So when you actually get to the most the environment can sustain, there is no growth in the population. It can't grow anymore. Same thing over here. Over here, look at 0. If there's none to begin with, if x equals 0, well, no more can become. Right? Yeah, exactly. Yeah. No way. Not through any means we know of in this physical world. And same thing here, if there's 2,000 rabbits, there will be a growth rate of 0. They just stop. And then there's 2,000 rabbits forever. Because this is an equilibrium. This is an equilibrium. This is an equilibrium. I think I said rabbits, but I meant sheep. Probably doesn't matter a whole lot. I'm just talking about critters in general. Critter 1, critter 2. Okay, so let's look at what these things actually do. So now I've got, come back to this x dot model. Here, you understand that. Notice that each sheep that is born decreases the carrying capacity. So I could actually rewrite this like this. It's x dot equals x times 3 minus the quantity. Yeah, let's just do that. I think that actually might make sense. So each sheep that is in existence diminishes the carrying capacity by a factor of 2. So each sheep takes more resources, so there's less room for rabbits. And conversely, y dot equals y times 2 minus x plus y. Each, I did it back here. That's why I wanted y plus x. Each rabbit that comes into existence affects the sheep population less intensely than each rabbit affects each sheep, whatever. This doesn't even make sense. Okay. I just keep getting confused about who's who. But there's a different effect for the more of the one population than there is for the other. And that's about it. These are not coupled, these are coupled systems. So notice these two things are highly dependent upon each other. These are coupled. And so our goal on Wednesday when we come in is to understand what happens. What are the possible scenarios for population growth in that little field up there? What do we expect to happen? Can they reach a happy balance? Is there a happy equilibrium where they can both exist, or will one drive the other to extinction? We'll figure that out. Yeah, cool. Sheep got the I eat more, get out of my way advantage. Rabbits got the but I am more advantage. Which of those two? How does that play? How do these two things interact? And so that's what we're going to do on Wednesday. And that's all I got for you. Has anybody seen this before? Bio class or anything? You have? Yeah.
It's like a simple version, but yeah.
Oh, cool. Where'd you see it at, Sophia?
In biology class.
Oh, nice. Was that like an advanced bio or?
No, Gen Bio 1.
Nice.
Yeah,
Wow.
Yeah,
That's cool.
Formula.
That's sweet. Oh, you just got the formula.
Yeah.
Cool. You're just like gonna have such a deeper understanding of it all after this. That's beautiful. Yeah. Very excited. Ooh, that makes me very excited. If I couldn't, I could actually, I guess there's room for more excitement. All right, friends. So let's work the rest of the time. Either work on planar systems 2 or work on your phase portraits, but consult with me, please. That's why we're doing this. Don't work on other stuff. That's all I ask, that you don't work on other stuff. No, you're not. You're doing great, Larson. You're all good. Oh, thank you. No one needs to pull their chairs in, just a heads up. Everything's great. You just like default polite.
Yeah.
Yeah, I know the feeling. Oh, just stop it. Stop scooting in. No, oh, there you go. That's there. You give me a challenge. I'm gonna do my classic bathroom run and then be back. Lou, you had a question for me via email. Does anybody need more light? Y'all good in the back? Want to strain your eyes as much as possible? Cool. Let me just help you. Yes. Okay. Good. That's good. Awesome. I'm glad that was good. Let me know that in the future, please. Yes, sir. I want you happy. I want you healthy. All right. What was your question? Because that sounded to me like the process what you were describing was right.
Yeah, but like, I feel like I get to like a, kind of a standstill, like, this process.
You have like this southern accent that comes out. It's like staying still. I like it. Sometimes I get to staying still. And derivatives.
Really?
Honestly, I've never even heard it before until just that moment, but I like it.
Well,
I like southern accent, frankly. Yeah.
I'm not sure if
What incarnation are you talking about?
I'm fixing to see I'm not sure that all
Dukes
the
of
numbers are
differentiation.
the numbers, you know.
So, actually, one thing you're doing wrong is what?
No.
So the eigenvalues are -4 and -4, right? So it's -4.
Yes.
When you subtract that off, you don't get that. That's right. I now remember. I was like, oh shit. Well, that's something I need to tell you. That's much better. Yeah. So that's gonna work from there,
Okay.
and then I'll come check. Yeah, probably gonna be a lot better. Is somebody doing okay? Anything I can help you with? Just get rolling. Okay, cool. Lou, you doing all right? Good, good stuff. Grayson, you getting your bearings or something I can help you with?
For this problem, I guess I don't know where to go from here. I've given this, matrix, I found the determinant, the u-vectors, the eigen, the inverse.
Okay.
I forgot what I'm supposed to do.
Well, you'll have to go look at that lecture. That is on repeated, what are your eigenvalues? Tell me that first, because I think.
I just got 3.
It's three is twice, right?
Yeah.
Three. So look at the process. Well, it's the same as 1. You did 1, right? Or did you not do 1?
I think
Looks like
the,
you got
the
1.
first one are you talking about? Like,
Yeah.
no, I left some of them blank.
Okay. Oh wait, this is planar systems 1, sorry, this is the first.
You meant the problem one?
Yes.
Oh, I didn't finish
Good
problem
lord,
either.
yeah, you really
I
tried.
got this one wrong too.
Damn. Yeah, you need to use the process, and it's a very different process. So let me see, can I see your notes and I'll help you find it?
Oh yeah, this is just what I gathered for that one because I do a lot of scratch. And it just-
It's a more involved, it's a quite involved process, that's why I'm going to make you go look at it.
I see. I kind of don't remember which
Do
lecture.
you remember the W vector? Let's see, may I just?
Yeah, go for it. Because
So-
it's linear algebra too, so I kind of forget
Yeah.
which is which.
And then you have to make a W vector.
Oh, you're also taking linear algebra? Okay, well I can see that getting mixed up in
It's not
there.
on the same time as the first one.
I don't remember which ones.
No, I think that's the deal.
It's this case, but I don't see it in your notes.
That's the one.
Yeah.
You didn't miss class though, did you? Or did you miss a class? Here we go. Here it is, here's the process.
That one?
This is how you do
Okay.
it, just like that.
Gotcha.
Yeah. Helps to know that for sure.
So when I walk down this way, help you with anything, that's not matrix.
You good?
I'm
Oh,
good.
you think catching up,
Yeah, I
okay.
finished the web work stuff, so I'll be
Awesome.
watching Wednesdays to try to.
In that,
That's
just general,
excellent plan.
or
Okay, do that, and that gives you the multiple of D1.
Which, so let me see
Yeah, to do
what's,
that.
we're on, this is, okay, cool.
1 over that value.
Is this problem 2?
Divided by D1.
Problem 1.
I
So
had
what
to
were your
rewrite
items
this
out?
out to understand my answer.
So,
You could
cool, so did you go through the generalized eigenvalue process with the W and all that stuff? 'Cause that's the only way to do this.
This values alpha.
So this is a repeated eigenvalue, and so this is the thing with the general, you don't get a second eigenvector. And so I'm not quite, I don't know, that probably isn't gonna work, okay? So you have to actually produce a pseudo eigenvector for your second one. And that's the whole process of the W, and then the 1 over alpha W, and I don't think you missed this, guys, definitely not. I think you missed the stuff on the tau delta thing. You weren't here last Wednesday. You doing all right? Yeah. Okay, cool. So it was probably the lecture right before that, honestly. I don't know where your notes are at. Do you have any notes? Yeah, there's something. If you get your notes out and let me show you where you look. Cause it's pretty involved.
Yeah.
Okay, it's okay. Well, that's not good. So yeah, it's gonna be it's a lot more complicated process. Let me see if I can do you mind, you find me a browser, I don't want people looking at what browser tabs I got pulled up, I don't wanna look at yours. Okay. So, we don't want it's not touchscreen, yeah. Oh, I bet this is good, this guy's got good notes. Yeah, he's going through it, that doesn't look super clear though, but that would be a resource. I mean, honestly, something you might wanna do is just go look at my example. Yeah, go check that out, definitely. Ooh, I hope we get a store. How's it working?
I'm trying to remember how to do this.
That's what today is for, yeah.
Uh,
Oh, don't do the extra credit, don't
No,
do the bonus,
no.
I'll extend the date on that too.
So it's on my town,
Mhm. No, yeah, and you don't go do that yet,
Okay.
for sure. So now you crank out tau squared minus 4 delta,
You find that value?
you find that value,
Okay.
and you need that chart, you're gonna definitely need that parabola graph. In fact, I'll just put it up on the board to help. But based upon the sign of this, so crank it all the way through, it's gonna be positive. Based upon the sign of that and where it sits in the tau delta plane along, so you also need the sign of tau, if it's positive or negative. Sorry, I just heard writing. That's cool. You can determine, based upon that graph, what you got there.
Okay.
So let me put that tau delta graph on the board for you, so you all got it. There was some extra credit assignment that was supposed to be next Monday, but frankly, you can just turn it in anytime before finals week, and that'll be fine. It's pretty involved. I'll put an outline of what you need to do to use this up here too. Do you all want to see like one more example of this? Would that help? Does anybody need to see an example of this? Are we good? Let me know, just like with the lights, I don't know.
I'd like to see it.
Thank you. Like I love a good communication between us. I'll finish the chart in a minute. Let's see here, so let me grab, yeah, I've got my good book. Let me wig something up here real quick. Well, okay, so let's say my system matrix is, let's do a little, oh, I can fake this out. I'll do 2 examples pretty quick. Whole process. So here's my system. X dot is 2x plus 2y. Y dot is negative y. Does that part make sense? I'm looking at that and knowing what my system looks like. Okay. Step 1, find the trace. Step 2, find the determinant. If the determinant is negative, you just hit the lottery. Because look at that plane over there. Anything that has a negative determinant, anytime this has a negative determinant, I've got 2 eigenvalues of opposite sign. So I have a saddle. I've got one incoming direction and one outgoing direction. So I know that since delta is negative, I don't have to do any more of, I don't have to worry about tau squared minus delta. This quantity only comes into play if delta is positive. If I don't have a saddle, then I gotta figure out where I am in the top of the plane. So I've got a saddle. If you have a saddle, and I did request this, if you have a saddle, find the eigenvectors and eigenvalues. So find the exact evals, which are easy. You've got this stuff right here, right now. So you just do that equation for your characteristic polynomial. Find the roots. Find the evals, evex, make a pretty sketch. But you know what it is. And everything that I've given you should have chill eigenvectors and eigenvalues. Only in the case of saddles, sources where both eigenvalues are positive, or sinks where both eigenvalues are negative, do you need to do this. So the only time you need to find them is here, here, or here. So let's do another example. Let's say A equals cheesing out. I'm cheesing out and making matrices where I can just read the eigenvalues. What are the eigenvalues of this system?
2, 3.
2, 3. They're on the diagonal, right? Because I've got a triangular matrix. So the eigenvalue is 2, 3. So I already know that, but I still want you to do this stuff. Find those two quantities. And now delta's positive. So I'm in the upper half plane. So now I got to figure out, am I here? Where am I? It could be on one of these lines as well. Then I crank out tau squared minus 4 delta. And that's going to be 25 minus 24 equals 1. That is a positive number. That is a positive quantity. So this region here, this entire region here is tau squared minus 4 delta is positive, and tau is positive. This region here is tau squared minus 4 delta is positive, and tau is negative. These are, everything on the right side in the top is unstable. The sign of tau determines stability. So this is all unstable stuff. This is all stable stuff. So I look at that, I know I have an unstable whatever's in this region, and what I said was in this region are, these are just source nodes. Unstable nodes. These are sink nodes. Over here. So this implies, I would say here, since tau is positive, tau squared minus 4 delta is positive, I have a source node. Find the eigenvalues. You've got all the ingredients. Hell, we could even factor that right here, but we already know what they are. They're just 2 and 3. Find the eigenvectors, make a pretty sketch. Okay. You've done this, honestly, you've done all the things that I'm asking you to do. The only new thing, oh, easy boy. The only new thing is using that damn chart and understanding that chart. It's going to become handy when we start getting into nonlinear things. I'll do one more. A equals 1, negative 1, let's see, 3, negative 1, 1, 0. Delta is 3. Tau is 1. So I'm actually sitting somewhere on this side, looks unstable. I just got to figure out where. So I find tau squared minus 4 delta. That turns out to be 1 minus 12 is negative 11. That is a negative value. Hence, I am in this pocket. So in this pocket here, these are the unstable spirals. Source spirals. These are the stable spirals. So in this region, this whole thing here, tau squared minus 4 delta is less than 0. Tau squared minus 4 delta is less than 0. These are stable spirals. I have so here I have an unstable spiral. Now your life is easy. You don't have to do anything. Don't find the eigenvalues. Don't find the eigenvectors. Go to the plane, get a few actual direction vectors in here to figure out what direction you're spinning, and make a spiral that is consistent with those. That's pretty bad, what I just did there. That looks pretty terrible. But everything in here looks like that then.
Where'd you get those arrows from?
I would have to go to the system that I had, Evan, so this one was, it's a good question. So I would pick like a point, let's say 3, 3. Plug that in, find out what x dot and y dot were, get those components of the velocity.
Okay.
That's about it. Yeah. So x dot positive is this way, y dot positive would be up, you know, and vice versa, all the permutations thereof. Does that help?
Yeah.
Cool. There's a lot of other cases here, but I actually did them in the lecture, so you can check them out. That's a wonderful words. Okay. Yeah.
So it worked.
Mm-hmm. Cool. Yeah.
Done this work.
Mm-hmm.
So, all of that.
Yep. That's not the form we used though. We gotta have the T in there now.
Right.
Okay, where's that T? How's that roll? Maybe you know even.
So,
So what you get for doing here?
Look at you using that fancy, sophisticated nomenclature. Look at you. Yes, yes. That there's city slicker, right? Yeah, that's your new. No, that's your new one. That is your new one. Yeah, looks great. Mhm. And there's also an E to the 3T.
Yeah, you can't get zeros.
Mm-hmm.
yeah,
Hold on, this is,
Yeah.
this is,
so,
what's it called?
oh, well,
This is finding the first even.
erasing that, actually. Erasing that.
So what's that vector look like?
The first one is 1, 0.
Yeah, let's put the actual vectors in, yeah. Yeah. Yep, beautiful, sorry, yeah. Sound doubtful, that's all right. Okay, cool. And that was your W, huh? This was, it was just 1, 0 after you did all the, okay, cool, okay. That's nice, that's handy. All right, so, so here they're just, actually, I mean, like, the 1, 0 goes, no, it's e to the 3t 0. So they want you to do the multiplication. And so that's e to the 3t times 1, e to the 3t times 0. You go in here. And then over here, I would combine these first into a single vector. So what do those combine to? So that it's just easier to see.
0, 1, and 1, 0.
Am I gonna be 1, 0?
It is not. Let's go slower.
Okay.
So it's 0, 1, let's write that down. So it's 0, 1, that vector. Let's just copy that down
Yeah.
somewhere. Oh, okay, anywhere, just scratch work, little scratch work, sorry. Okay, cool. And then let's multiply this t up, so plus,
No, it's 1, 0.
and then write t zero, 1 times t zero. Put the t inside the vector, that's what I'm trying to get you. So it's just easier in your mind once you start trying to combine them. Yeah,
And it would be,
yeah, cool. So it's gonna be 0 plus t on the top row, so t.
So then your
What's the bottom row?
1, so it's just,
Yeah, nice.
You can choose
Great.
a value.
And then that's times e to the 3t as well, so right up here, because we had that c2 e to the 3t.
So your W is
is it
0,
0, 1?
Yep. Yep, so what's your top row? You've got c2 times what?
Top row
Yeah.
is
Uh,
C1.
yes.
It should be. Yeah.
And that's
Yeah, I like this, lowercase, yeah. What do you know? There you go. That's beautiful. I don't know about that.
You don't know about that?
I don't know about that. I like the top row, I don't like that bottom row at all. I don't think you're even writing down what you wrote there on the paper.
Am I not?
Wait, oh, I'm sorry, you're right. Okay, I was thinking of that 0, you're right. Let me see. It is like the very blunt. Neither of the solutions is correct. So maybe your eigenvectors are wrong. Let's look into that.
I mean, my eigenvectors are wrong.
Oh, right. So what is it saying wrong? Oh, it's saying that's wrong. Okay, so. What? Hey, Evan. That problem we were looking at earlier today where it was like, you got it right, but the answer was insane that Webwork wanted. What problem was that? Do you remember?
5.
That was 5 on the first assignment, okay. Yeah, okay.
On planers 2.
Okay.
Oh, yeah, no, sorry, the planers 1.
It was planers 1, number 5. Okay, cool, thank you. So that's not, okay, because there was one that was given Evan a lot of grief where he did not deserve any grief. I mean,
Maybe it wants us to do
oh, and Lou, hold on, what's your eigenvalue?
-1.
What does that look like? I think we
That
found our
is-
problem. That is whack-a-mole.
Insanity.
Why do I have a feeling this is gonna work? Alright. Now you can find the C1 and C2 as well.
Yeah.
Yeah, okay. Now you're rolling. Cormac, can I help you with anything, friend?
Maybe.
Cool.
I think I'm just entering this drawing.
Are you doing it on your phone?
Yeah, I forgot.
Wow. Do you wanna work up there?
No, I'm
Okay, alright, would you like to be in the center of everything where everyone can just watch you do your work?
I think that's a little scary.
Yeah, it's a little scary, yeah. Okay, so may I
Yeah.
take a look at what's going on here? Okay, so we found, so this is our thing, and lambda's 3, and then that goes to -2, yeah, that'll, looks right, yeah, okay, so that's good, and then, this doesn't seem right. Wait, what is that number at the bottom? It's hard to tell.
-1.
Ah, this is not right.
Okay.
Oh wait, no it is, that's a 1 there, I thought that was a -1. Okay, so you picked some point not on that line, right?
Mhm.
What was that you picked? What, to find the W, you have to pick something off of.
Oh, I thought W is what you pick, and then you pick.
No, well, no, Yes, you're right, sorry, I'm like, my own freaking problem. Okay, so you pick -1, and then you ran that through that guy, and so then you get 4 negative, what, yeah, 4 negative 4, okay. Cool, oh, so that's 1/4, so 1/4 was your factor that you put in front of the W, so it was -1/4, -1/4, that looks beautiful.
More like,
And then, wow, that looks great to me.
okay, I'll just double check that.
Do you want me to look at what you got there?
Take your matrix.
This looks
factor
solid.
from the E value.
Mhm.
And then
It's-
turn into an equation.
That's what it, yeah.
And then you just like choose.
Yeah, it looks like you
one.
have a T, it looks like a parentheses,
Oh,
because that
yeah.
shouldn't be there, I think that's your problem. That's where it is. Cool, easy, good work, you're welcome. No. You're welcome. Okay, cool, find that process for me in your notes.
Like the second one.
Beautiful, let's go through it. Is this your work for this one right here?
No.
No.
That was the first.
Okay, do you have work for this one, or you not? You do? Awesome, okay, yeah, that's what I really wanna see.
Well,
Yeah, yeah.
no, for like these two.
Ooh, was that your math major, whiteboard or something? No, you, I gave you that, yeah.
Oh, no, I had it at home, I just.
Okay,
decided it.
cool. Alright, good work. Beautiful. Okay. So we'll go through the process, so you found -6 was your, yeah, -6 was your eigenvalue. And did you get a vector for that? What was that vector? 1, 0, that sounds beautiful. So you picked that guy who's not on there, love it,
Yeah.
and then you ran it through there.
So see
that. I think you didn't run it through there right, and that's the problem. I think you're doing everything right. What is that?
That's right.
So do that top row again.
What's the solution?
No, it's okay. Take your time. Yeah, so it's dot product of first row with the column. There you go. What do you have? Mhm.
Okay.
There you go. Yeah, exactly. Yes, definitely. So then, yeah, but something seems off there. Because. Oh no, this is great. You're right. Actually, you're totally. Can I? Yeah, right. Because we know that that's a 1. So then you look and see what multiple is this of the original eigenvector. And the original eigenvector you had was 1, 0. So the multiple is 1. So your alpha is 1. And then when you, so your V2 is 1 over that multiple the other way. So it's just literally, V2 is that.
Okay.
That's your V2. There you go. Does that make sense?
Okay.
There you go. Yeah, keep on cranking, I'll come check on you. Good work.
Okay.
Yeah, you totally can, absolutely.
When it says convert the system to a second.
Oh my gosh, yeah, I hate that, that's,
What could we just do with this?
don't even do it, yes, please. That is, on planar systems 2, problem 3, ignore the convert this system, please. We'll do that later, like it doesn't even matter, but on planar systems 2, problem 3, it says, convert the system to a second order diff EQ. Just do that the way we've been doing it. You'll be fine.
Okay.
Yeah, good question, thank you, actually, that's super helpful to a lot of people. Daniela, hi. What can I do for you? Okay, cool, so you got your process all out here, this looks good. So, okay. So, you're cool on the V1 and everything, yeah? Oh, okay. So we find go through and find one eigenvalue in the way we've always done it. In fact, you can read it right off the matrix. What's one eigenvalue? Solid. Find an eigenvector for that. That is V1. So this V1 here, that's the eigenvector you just found. Then pick any vector that's not a multiple of that. Any one at all. Run that through, take this matrix up here, multiply that, because this thing here is just that right there. So pick one, so give me one, let's do one together. Let's do this together. So, because we need to write, otherwise it's just, I'm just kind of talking and it might start to sound like mush. So let's find the first eigenvector. Oh, beautiful, okay, that's great. That is great. So what would be another vector that's going to be our W that's not a multiple of that one? What would you like to use? Yeah, perfect, cool. So let's write that down. So let's let W be 0, 1. Very nice. Now, so to find that, we need to subtract the eigenvalue. You know the matrix you used to find that first eigenvector, which would be 0, 1, 0, 0. We're going to multiply that times this thing we just created. So that's what this is saying right here. Compute blah times W. So let's do that next. Does that make sense what I'm saying? This is why we need to write it, right? Because there's just too much going on. Beautiful. Times. Yeah. Yes, ma'am. Now what's that give us?
0.
It does not. But you wouldn't be the first one today to think so. What is it actually? Let's slow down. So how'd you get the first row? Yeah, so 0 times 0 plus 1, yes. Very nice. Yes, ma'am. Cool. Okay, so that is, now we're at this stage here. So we compare what just came out to the original eigenvector V1, which isn't written. Let's write it up here so that, yeah. Awesome. So what do you have to multiply V1 by to get W? 1. So that's the alpha that's right here. This thing that comes out will be a multiple of your first eigenvector. Whatever that multiple is, that's this alpha in front. So for us it's 1. And then we take 1 over that times our original W, which doesn't change it in this case, right? So W, and maybe just write this here so that you have it for the next problem, right? So 1 over alpha W. And that's our V2. So that is V2. So try that, and that should work. It's pretty, just easy tweak. You can probably change it up here too. And then, in fact, definitely, we're gonna have to do more to get that. It's that guy right there.
Oh, I thought this one was correct, right?
Say that again.
This one was correct, right?
It was? What? Can I see the original problem? I want to make sure we're on the problem that I think we're on. It was -3, -3. I don't know. I mean, there's actually lots of possible answers. I guess that's... Can we just enter this one that we put in just to see? Because that's a little disconcerting.
This one?
Yes, ma'am. How did you get get that first one, by the way?
Well, I just did the row.
Yeah, I don't know, that worked out amazing. It seems like it was just like, was that one, wasn't it? Yeah, but what the hell is going on here? Okay. Okay, so we got -3, that's great. And then, oh, maybe that V1. I think this is wrong. That's the problem, I mean, these can't be the same. So let's go back, do you mind if I write on here? Okay, cool. So let's go back and find the, so for lambda equals -3. Help me, Daniela, help me. Okay. Oh my God, that's awesome. I can't believe that works like that. So then we'll get our matrix, and it's gonna go to subtract -3 off, so it's 0, 1, 0, 0. And then times x, y equals 0, 0. Pretty slaughtered. But that means, yeah. Okay. The W is this. We didn't take, this should be 1 over alpha. The alpha was 1, it should be 0, 1 here. That's the problem. We miscopied the W because it's whatever that multiple is times this thing right here. So that should be 0, 1. Yeah, that's the problem. Now it's gonna be okay.
This one's correct.
Yeah, good, yay, right on. So now, once we do all this, you just get your V2. So your V2 is the 1 over alpha. You already got it there. And whatever. Now let me try your thing. Yeah, why don't you take over? Oh, beautiful. That's the kind of function I was looking for. So your solution is going to be C1 V1 e to the lambda 1t, so -3t plus C2, and then here this is going to be V2 plus t times V1 e to the -3t. So you've got everything you need, now you just got to kind of put it together like this. Does that make sense? Give it a shot, and I'll come check on you when. Oh, yeah, yes ma'am. Yeah, you're just gonna put in the V1 e to the -3t part. So this will definitely have an e to the -3t in it, but it will also have this part, so there'll be a t in there as well. Yeah, I would write this all out and kind of like, it's definitely hard to do in your head. I'll come check on you again. Thank you. Are we doing something I can help with?
Yeah.
Oh, it sounds like it. Cool. Let me join the party.
So I got this side. I'm just trying to get this side now.
Okay, so this is -4. There definitely should be a T, and there is a T in there. Okay. Can I see your one?
Yeah. Right now, I mean,
It's a little
not
rough.
Yeah.
Yeah.
I kind of did it.
Okay, so this will not have a times T in it for sure. So there's
And,
something a
I
little
mean, it
weird
said it's
there.
correct there, which is weird.
Yeah, that's insane. Here, can you see this?
Yeah.
Okay, so what was your original eigenvector? Okay, cool. So we got 1, 0, and then these are both correct. Okay, so then V2, after you found that, was 0, 1. So your solution is going to look like this. It's going to be C1 V1 e to the -4t. See, there's no t there, so I don't know what they're talking about, but it's not the first time it's been weird. And then this is going to be C2 times V2 plus t times V1
think that's what I did here, cause if you do that, then the T is plus 0.
Yeah, it's probably thinking you did that for that one. It'll probably take them in either, so it can't be in both.
Oh, okay. I got it.
So like, let's just do it together here. So we got C1, 1, 0, e to the negative 4t plus C2, and then this guy's gonna be V2's 1 plus 0t from that, so because I multiplied that by t, and then I'm gonna have 0 plus t e to the negative 4t.
Okay. Okay, so.
Is that, yeah.
Yeah. That's what I did.
Yeah, I would change both those just to be, because I think it's not gonna like it.
Yeah.
Yeah, I don't know why I don't know why it's telling you
Okay.
that part. I think that we got it now.
Yeah.
Yeah, yes, can I help you out?
Once I get to know vectors, I'm not sure if I'm following what
What were your eigenvalues? -4, -1. Yeah, so can we go back? So it's looking good. At this point, let me come up on the board and do this, because then it'll be on the recording. You're so close. We'll probably take some time on Wednesday to work too. Do a little new material, do a little work. So you got lambdas -4 and -1. And so this is your slow, this one's your fast, magnitude-wise. So let's say, let's say that's the vector for this guy, that's the -4 vector, and then let's say this, and I'm making it a little different than what you have. And then this is the lambda 2. So this is lambda 1, this is lambda 2. So lambda 2 is my slow, so this V2 is my slow direction, and they're both incoming, just like you said. Ooh. So they're both stable directions. So you become parallel to the fast direction as you move away, you become tangential to the slow direction. So in other words, I'm going to approach this V2 tangentially when I come into it and be parallel to this guy when I'm far out. So my trajectories are going to look parabolic, kind of warped parabolas, but notice how they're tangent to the slow direction.
Why is that?
It's the way it works out.
So the slow will that always be the case for fast and slow?
Yes, always.
Would be tangential to the slow and.
Even if this was +4 and this was +1, exact same picture, except in opposite direction.
Okay. Okay.
Does that make some sense?
Yeah.
Yeah, so tangent to that slow direction, eventually, then parallel to the fast as you move away.
Does it matter where the line starts?
Which line?
The parabolic line?
No, I mean, just enough, nah, doesn't matter.
Okay.
Yeah, we're just doing qualitative here. Hi, can I help you with? Yeah. Do you need more time on it? You don't want this, okay, yeah, okay, gotcha, yeah. Okay, cool. I see, that's good though, that's good. Yeah, it can be painful, that's cool. So then the other thing that's, and it's probably too late to start on it now, but there's those phase portraits to plot. Yeah, thing I talked about at the beginning of the hour, looking to go to world class. Those are due on Monday. Go to the calendar right there. said, click on the home. Yes, sir. I'm sorry. Yeah, next Monday. Yeah, yeah. You thought I was saying something else. Okay. Oh, no. Yeah, you better you got like 3 minutes, man. Get cracking. No, next Monday. You got plenty of time. But it's that stuff. Okay. So be sure to watch the examples of how I approach them. Okay. Well, hey, Tracy.
I'm on this problem here, and I've gotten to this point, and I don't know where to go. So, given this, I found the eval, the e-vectors, and the C1 and C2. I just don't know what I do.
Okay.
This one up here.
Okay.
Yeah, so I plugged in the initials, and the C's, and I set up this with the...
Okay, yeah, let's go from the, let's just kind of go through everything and make sure. So we get -3, -5. So you got these E vectors and I'm just checking them in my head. That one looks good. 6 So what were your eigenvalues?
Right
What are those
here.
guys?
Maybe 2 and -3.
Oh, okay, okay, got it, yeah. I'm just trying to set this one -2, 3, so that gives you. Oh, right, okay, that looks cool. And then this guy this should be -9, I'm just like, I'm trying to do the math. You've got -6. Okay, cool, groovy, those are totally correct, yes, so this stuff is all good, so you're almost home free.
Because I set up here for the initial, and I got the
And I
C's,
messed
and then...
up.
Yeah,
right in
just so, I mean, just put it
Yeah,
now
I had
back
to go
in
back and like
to
re-look through all this. I was like,
to your solution vector, let's just write it
it's all
in vector
such
form.
tedious, like if you're not careful doing it when you're tired.
CT.
And again. And again.
V2. So you just have to rewrite this
Yeah,
all
hopefully
out,
that's
so
it
it's
if you're
C1,
lucky.
e to the, whatever that is, -13,
Yeah.
e to the -2t times that vector, -1, 1, C2, e to the -3t.
And then that's how I found xt, and then how do I find the water t?
Well, this is both.
Oh.
They're just the different rows of the solution, so -2, 3. So for example, the x of t is C1 e to the -2t times -1 plus C2 e to the -3t times -2.
Oh, I see.
You see what I mean?
And the
Just
Y's
kind of
in
read,
the-
yeah, the y's
And
the
then I
bottom
just
row.
fill it in.
Yeah, and you got all the work
And
done.
then I can I just plug in like 0 for t.
You've already done that. If you found these and these are right,
Oh, well,
you kind of already did it,
I
which
guess
is
that's
amazing in some ways. So like part of you knew this,
Yeah.
and then part of you forgot it.
Yeah.
So to get that, you had to know that.
Okay, that makes sense.
Yeah?
Yeah.
Awesome.
Okay, thank you.
You're welcome. Sarah, how you doing, friend?
Pretty good, it's making sense.
Okay, good.
Yeah.
Yes, we can only ask for that. Lou, you look cool.
It's really small. Oh. A,
Mm-hmm.
and then
Mm-hmm.
down to V1.
I agree with that. And then you picked
And
a
then-
W that's not on there. I like it.
And then
You multiplied that by that beast, and that gave you -4. Oh no, sorry, it gave you -2.
and 2.
I see.
And then the alpha is
The alpha is 2, so
So-
V1 is 1/2 of W. 1/2 of W. You're using the original eigenvector, that should be 1, 0 then. That's your only problem?
Okay.
Yeah?
Okay.
I
You
have
need-
one question.
You got it, yes ma'am.
It's probably like kind of trivial, but when I'm labeling it, do you care where it is as long as it's in the section?
Yeah,
Or
you
should it
didn't
be, like-
even really need to address this, but you didn't need to have this beautiful portrait, but I love it, so
Okay.
please keep it.
Okay,
You can just tell me just
Okay.
give me the signs and I know this picture in my head very
Okay,
well,
so like what I said here. where-
it's beautiful.
Okay.
Yeah,
alright,
this is great.
Cool.
Yeah,
Okay,
Awesome.
I just wasn't
Hi,
sure.
bye, bye Tracy. Is that, you're good?
Yeah, that's
Awesome,
all.
yeah, it's lovely. You good? Yep. Great. Alrighty, friends. Cecil, you good? You got anything? Okay. I'll be seeing you soon anyway.
It still says that.
Hold on. Oh, this. See, I look at that and I look at that and that makes me worry about you. Concern. Good. Comments have been. I don't really have any. All good, except there's an asterisk there, and it's because of me checking on it all the time, right? Right. So I'm just putting that there. I would put ish. I think that's true.
Dr. Smith, this last C value is not being recognized.
Oh, let's see. Okay, everything's good.
Yes.
Okay, so, let's see, so your initial conditions, one,
Yeah.
one, -1, so that's supposed to be a 1, so you put in 0.
So the bottom C2 should be -4. I mean,
Do this. So, okay, so we put in 0, and get C1, 0, C2, 0, 1. Is that, would you agree with that? Because T is 0, right, so that kills off, oh, come on in, Camille.
yeah.
It's all good. So C1's just gonna be 1. Bye. And C2's -1.
Oh.
So I don't know. I don't know where that all came from. Does this make sense?
Yeah.
Yeah, I don't know about that too. I'm gonna go talk to Luke, check that out. Oh, yes, hold on, yes, yes, did you have a second?
Yes.
Okay, cool.
So this, bad,
Wait a minute, what is this say?
this, so
Yeah,
this
yeah,